Okay, hello everybody. I will do a presentation of my current work in underwater networking. I've been working quite intensely the last couple of weeks to submit a paper on my current work, which I will present here. Just like Clemens and Ariel, I am also concerned with energy consumption, but in networks. And this in order to enhance the endurance or lifetime of the networks. So, with the current trends, or what we are looking in, if we are looking into a bit into the future, the size of networks are increasing. The number of nodes participating are increasing, and we are introducing more autonomous vehicles. So what I have been looking at is a little bit larger network, and you can see here, this is the sort of network I am currently looking at and simulating. The idea behind this is that we have a network, a quite large network of both static and moving nodes, although I'm only simulating with static nodes. And with the classic strategy for routing information in a network like this would be to determine routing tables in all nodes. You have to share, all the nodes has to know all the other nodes location in the network topology, so to say. This sort of strategy requires a lot of time and energy to just set up the network. So for instance, if we have this node number 1 here, which would be a source node, maybe a sensor that want to send some data to the sink, with number 16 here, which we could imagine being an AUV or something. This would mean that the routing protocol had to, in advance, decide on all the possible routes and decide on a best route to the sink. This sort of strategy is very slow and energy consuming, especially when networks become of this size. They are bad at scaling up, and with the new dynamics that we have in the networks due to moving vessels and picking up and deploying new sensors, this wouldn't work anymore. So I have implemented, there is another type of routing protocols which use very little overhead and doesn't require any topology information to be disseminated through the network, which makes it a lot more tolerant to dynamics of the network and are more scalable to size. So I've been implementing one available flooding protocol, which they are called. They in the simplest sense, any node will forward any message that it receives, and until the message ends up at the destination. But I have, based on some previous works from people at FFI in Norway, I have implemented their flooding protocol, which adds some constraints to the forwarding process, which in turn reduces the amount of transmissions in the network. This, of course, saves some energy and reduces collisions if there is a lot of traffic going on. But this type of protocols are still retransmitting a lot of packets, which is energy consuming. So I have been looking at an add-on protocol to use in parallel with this protocol that is supposed to reduce the energy consumption in the network. And my approach has been to calibrate the transmission powers of all the nodes in the networks. This is done in a pairwise manner, so each possible link, as a node in the network detects neighboring nodes, it will try to calibrate its transmission power with each neighboring node. And then all the nodes will in this manner build up a record with its neighbors and what sort of transmission power it requires to transmit to the neighbors. And then as payload messages are to be sent or disseminated through the network, nodes can use their record of calibrated transmission power and choose a suitable power level adaptively. My strategy in the current work is to use a very simple approach and just select the among a node's neighbors, it selects the third smallest transmission power. This is sort of to guarantee that a packet will move forward in the network and not end up in sort of dead ends, because a really small transmission power, then a packet would just start bouncing between two nodes. On the other hand, if you selected so that a lot of neighbors should get the packet, then you would of course not save very much energy. So to continue, I have implemented these strategies, and I'm performing simulations in a framework called Unetstack. This framework allows me to simulate the protocols and evaluate their performance, and then implement them and do in situ trials on these acoustic modems that we have received from Subnero, a small company in Singapore. So we have a few of these for future validation of the protocols. So the whole point of this is that I can take the same code I'm running in simulations and put in the nodes for validation. So this is a simulation of one of these networks where I have, like in the node placements in the previous figure, I'm running a calibration. In the beginning, all the nodes are calibrating their transmission power levels, and then node number 1, the source, is transmitting 500 packets that is destined to the sink, which was number 16 at the opposite side of the network. And what we see here is a time scale. It's during a pretty long time, and an energy. So this is essentially the energy up to 10,000 seconds here. This is where the calibrations are completed. We see how much energy that the calibrations themselves have consumed. And then after at t equals 15,000 seconds, we begin to transmit the payload packages. This is how the process looks like for one simulation, how the energy cost is. But if we do this for multiple simulations, we can move Okay, now let's look at this first. So if we do this for 20 simulations, 10 without my add-on protocol, which means that all the nodes will transmit at full power all the time, and 10 with my add-on protocol, which performs the power calibrations. And we can see that we get a pretty significant drop in the power consumption using this protocol. So this is the power consumed for the 500 packets. So the energy averaged over the time of duration of the transmissions. So we have at least halved the power consumption, while we can see here in the figure to the right, this shows the packet delivery ratios. So how many percentage of the transmitted packets actually arrive at the destination. We can see that without my add-on protocol, we are at around 90% delivery. While with my protocol, we can assume that the delivery rate will be reduced a little bit, since we are actually lowering the signal power and making it more difficult for modems to hear packets. But we can still see that it is not affected all that much. If the network endurance is a priority, we can definitely accept a small drop in packet deliveries. However, we have this worst case scenario where D-power can actually cause a significant drop, which we will look at closer. But here we can see roughly how the network connectivity looks like with and without my add-on protocol. So here I count the number of packets received by each node to visualize how the traffic looks like in the network. So this is for the same scenario. We're transmitting 500 packets from node number 1 down to the left to the sink, which is node number 16 up in the right. And we can see that with my calibration procedure, that the connectivity is reduced, so a lot less overhearing of messages is done. This likely means that we also reduce the number of collisions in the network a lot. So in this scenario to the left, if packets are transmitted frequently, you get a lot of collisions in the nodes. So it could be that at some rate that my protocol actually reduces the transmissions and improves the PDR. Yeah, but of course, since we are transmitting at a lower power level, the packets are forced to take additional jumps to the destination. So instead of being able to make these long jumps, it has to make several jumps. We can see that because of this, that the delay from the source to the destination is increased, and also that now packets may take different ways to the destination, which causes a sort of you get a bigger spread in the delay as well. So we had roughly 40 seconds of delay from source to destination, and with we have about doubled it to around 100. So here we have this worst case scenario that we saw here. This is a similar scenario to this one, where we get a severe drop in delivery. This may happen when we have these clusters of nodes that are calibrating after the transmission power levels has been calibrated, and when selecting a power level for transmission or forwarding of a packet, because we have nodes that are very close to each other, they will always select a small power level. And this can cause this separation of the network. Of course, we have some ideas on how to solve this for future, but that's up for future investigation. So in Outlook, we are going to validate these protocols in actual sea trials. We are going to Kristineberg, and there we are going to try a smaller network with 5 nodes or 5 static nodes and 1 node that we are integrating into Lolo, the AUV. This will allow us to validate this in a real world scenario. And we're also going to try out one or a couple of strategies to go around these black hole clusters problems that we have seen. Yes, I think that is it for me. Thank you.